integrated circuit, 17 digital circuit. Multiplier. The multiplier is the important part of CPU component nowadays. Every CPU has the hardware multiplier. How you make a multiplier is a subject here. The multiplier is basically AND gate, but if you have full adder, you have carry in A, B, and carry out and SAM. Okay, so when you have 32-bit, for example here, and 32-bit, okay, every combination has to go through this, the full adders, right? So what happens is you're going to create, say if number of bit is n, then result is going to be 2n, right? Now let's count number of input. Number of input here in the beginning for full adder, you get 3 and you get a 2. So each stage of adder, you're going to add everything in this area, this region. So that's called Wallace Tree method. Okay, so every full adder reduce 3 input to 2 input. So it's going to be n stage necessary. Okay, the n stage, the total number of input is going to be here 3 times n square, right? And that's become the input to the last stage is going to be the 3 2n. The last stage, the result is 2n wide, and the last stage will have only only one left. So this is 2n, right? So what's happened is, if you take a log, the n disappear, 2 over 3 n equals n log to 3. So number of stage you need is going to be divided by log to 3, and this number of stage is going to determine the propagation delay from the data in the register all the way to the result coming out. Okay, and it's going to get pretty long. The Wallace tree, you add this, you add this, and you add this, and you have to add from this guy, and you have to add from this guy. It's going to get less and less because number of adder you have to perform is n square, and the number of input is like a 3 n square, like this, right? So in order to reduce down to last 2n output, which is the SAM, which is a result of multiplication, you need to go through this many stage, and that's going to be the delay time from multiplier A, B, and C. Okay, so 64-bit double precision is going to be quite a lot. Say you have a 32-bit multiplier hardware, which is a lot of hardware in the CPU. It's bigger than ALU. Okay, so 32-bit multiplier, what you do is, when you do 64-bit multiplication, you have to divide into the section 64, divide into 2 sections, and you have to multiply with this, multiply with this, and multiply with this, and multiply with this. So 64-bit hardware Wallace Tree is going to be huge hardware. It's just same hardware repeated so many times, and it's just work like this. The end result is 2n, and the beginning is n square. Okay, so the realistically using 32-bit multiplier, you have to repeat this operation once. So how many you have to repeat? 4 times 4, 16 times multiplication, and the result has to be all add up again. So multiply 16 times, and result will be add up using ALU. So multiplication is quite a big operation. Okay, so this is the kind of problem we're facing when the word size get bigger. 64-bit, we divide into 32 each and multiply each part and add them all, aligning and add them all by ALU. So if multiplication of 32 is slow times 16 times and ALU delay, so 64-bit multiplication is going to be so slow to perform in ALU. So nowadays, since integration is so high, nowadays ALU has a 64 multiplication unit. But even that, in order to make it pipeline, you have a long register, and intermediate result is stored in the register, and they are added again. Why you do that? Because if you shorten this part n nanosecond, okay, then the clock can be n nanosecond to get the result, and you can use a pipeline. That means you have to multiply many things: A times B, C times D, E times F. So you can pipeline operation. So every n nanosecond you can get the result. Okay, so that's quite a lot of hardware. So you look at the CPU chip. The major portion is register. You have many registers these days. A, B, C, D, E, F. The old one got only 4 or 6 registers. Nowadays it has 16 registers. Register is each one is a flip-flop, and it's cost a lot of hardware. So the register is big. The multiplier is even bigger. 64-bit multiply is much bigger on the CPU chip. You see the CPU chip, big portion in the middle is like a multiplier, and the register. The ALU is moderate size. Okay, and instruction decoder is like you cannot even see it. It's somewhere, right? And the cache memory is big. Depend on how much cache on chip. you put. So those are all the real estate used. The silicon real estate is used by multiplier, cache, register, those stuff. Okay, remaining is just random logic. You cannot even identify where they are. Okay, so I hope you like this video. If you like, subscribe.